Hello. In today's project, we will add customized layers on top of a pre-trained Huggingface BERT to make a transfer learning classification model for text sentiment analysis. I do want to say in the first place that if additional customization is not needed, if you just want to do it in the quick way, then Huggingface actually has a pre-trained classification model ready, such as the auto model for sequence classification. But this is not our topic today. This model will just do the same thing as the projects that we are doing today will do. And today we will demonstrate how to build and train the transfer learning model with the Keras Functional API. We actually chose to build on the DistilBERT instead of BERT due to its smaller size that doesn't push our GPU to the limit. But there are other similar alternatives, such as BERT, LBERT, Roberta, and XLNet, which can be used interchangeably. So let's do a quick introduction about BERT. So BERT is the bidirectional encoder representations from transformers. If you are familiar with transformers, it involves an encoder and a decoder, and BERT only takes the encoder part. I can show you a diagram from Huggingface. So at the bottom of this model, you still have the word embedding plus the positional encoding computed from the input word index sequence. I think they omitted this part in the graph, but they are actually here. Then comes the multi-head attention, the layer norm, and the feed-forward blocks with the skip connections, which is the well-known architecture used in transformers. And they repeat this part of the encoder many times in series. For BERT base, the repetition is 12 times. For BERT large, it's 24 times. And for the model we are using, which is the DistilBERT, it's only 6. And it will only have about 66 million parameters. Actually, the DistilBERT is trained from the BERT model. And I selected this DistilBERT model due to its lightweight. Then I will show you another diagram in which I put more of the relevant information that we need to know when putting our additional layers on top of these models. So these inputs are actually integer indices of the tokenized words, and they can have a variable length. This block is the one that we have just discussed. And the output actually has the same length as the input. And the other dimension of the output is the embedding dimension, being 768 for BERT and DistilBERT. So we actually discard all the rest of the embeddings and only keep the zeroth one. Actually, we cannot use all the embeddings because they have a variable length. So we take this single embedding vector and we put a dense layer after it with the ReLU activation. And finally, it's our final dense layer for the 3 classes that we have. And the activation is the softmax. Actually, you can put any number of classes here, but we have 3. So yeah, in between, you can also add more of the dense layers if you want, and you can tune the dimensions of the dense layers. And of course, you can use dropouts on top of the dense layers. So yeah, as you can see, this is the advantage of building our actually customized model for classification, because you gain much more hyperparameters to tweak with. So now we can start coding. First of all, we download the packages that we need to use from Huggingface. And here we set some numbers. The embed dimension, which is the embed dimension inside the BERT or DistilBERT models, it's 768 by nature. And this max length, 32, this is the maximum length of our input sequences that we are going to use. You might feel this number is too small, but due to our GPU capacity, I decided to stick with this number. And yeah, we download our dataset from Huggingface. And this is the web page that shows some details about the dataset. Yeah, this is how it looks like. And we can download directly by this line. And we're using the auto tokenizer and this DistilBERT base with cased. Yeah, first of all, let's do some data exploration. Here shows the structure of our dataset. It has the train and test set already split for us. And we have these features. We are gonna use the text, which are the sentences, and the labels, which are 0 for negative, 1 for neutral, and 2 for positive. And these label text are these 3 words, negative, neutral, and positive. And we don't need them. We also don't need the IDs. These 2 are the only things we need. We want to make sure we have balanced volume for all the classes, and actually we do here. So fortunately, we don't need to take more time to duplicate the minority classes, and we don't need to worry too much about our model to get biased. Yeah, and here I want to show you how the tokenizer works. In order to turn the sentence into a sequence of integers to be recognizable by our models, they first turn it into a list of tokens. These are called tokens. They are not necessarily words, as there are some words broken down into some even finer parts for this word. And they also discard or swap some unrecognizable characters from the sentence. And then it will add what's called the CLS token to the beginning, which corresponds to an index of 101, and the SCP token to the end, corresponding to an index of 102. And they tokenize the sentence into the integers. So about this attention mask, we have not done padding yet, but what this does is that after you have done padding, it will put zeros in the places that you have padded your input indices. The purpose is to block the paddings from disturbing the multi-head attention blocks in the encoder part. And yeah, they will have the same length as your input IDs. So this is our function to pre-process our data. There are several things I need to point out. So first, we're not doing padding in this tokenizing step. We can, but we are not, because we want to do the what's called dynamic padding in order to save some memory and GPU power. The dynamic padding actually can only be done when batching. It pads separately for each batch, and only pad every batch to the maximum length of that batch. So we don't need to pad all the sentences to 32 tokens. And another thing is that we do have the overflowing here. What this does is instead of truncating the overlengthened sentences and discarding the rest part, it actually unrolls the overlengthened sentence into several parts with a stride. So you end up with several samples derived from one sample. And yeah, we replicate the labels for them. And here is our training and validation dataset after pre-processing. So each dataset is actually this dataset object from Huggingface. These input IDs, they are the lists of the tokenized sentences in integers. These labels are 0 or 1 or 2. And these attention masks, you see they are all ones because padding is not done yet. And the padding will be done the same way as for the input IDs, just to block the padding zeros. And this overflow actually tells from which original sentence is this sentence derived from. Then we will be creating our data loaders. And here it might look a little bit strange here because I'm importing another class, but I do want to clarify that I'm only using this class for preparing the data loaders, and right after generating the data loaders, I'm deleting it. So why did I introduce this class? That's because I want to use the prepare TF dataset function under this class. So the model that we are using, being the TF DistilBERT model, it also has this function, but will perform in a different way. So for this class, the prepare TF dataset function will return something like this, which includes the input IDs, which we need, the attention mask, which we also need, and it will also return our labels. It doesn't have a name here, but it's the labels, and it's recognizable by our training function. However, the prepare TF dataset function under the TF DistilBERT class will not return these labels, which will really be a headache for us because we really need the labels to be batched and turned into data loaders the same way as our inputs. So yeah, after this step, batching and dynamic padding is done, and we can just iterate the data loaders like this. So this part is our model. It's that short. So here we have our output from the BERT layer. We do a dropout and followed by a dense layer, just as I have described. And another dropout, then finally the output layer, followed by the softmax activation, just as I have described in the diagram. So here the BERT model is loaded from the pre-trained version with all the parameters being already trained. And the dense layers, the two dense layers we have added, they are actually random initiated. So when we are training the whole model, the BERT model actually gets fine-tuned. And the loss we are using is the sparse categorical cross-entropy loss. So what this does is that you have a label being an integer, 0, 1, or 2, and you have your output being 3 decimals between 0 and 1. It will automatically turn your integer label into a one-hot format, then compute the cross-entropy loss with your predictions. And yeah, this is the visualization for our model. These 65 million parameters are pre-trained from the DistilBERT, and these two are the customized dense layers added by us. This function is only used for validation and is directly taken from the Huggingface page. And here we have set some of the callbacks that functions through our training step. So in this training function, when we are using this model.fit function, remember that our dataset is in the data loaders is in such a structure. It's a tuple with the first element being a dictionary containing the input IDs and the attention mask, and the second element is the label. So this structure will be recognizable by the fit function. It is smart enough to select the correct elements from our data loaders. And yeah, finally, we yielded a validation accuracy of 99%, which looks really high. Finally, we proceed into our evaluation step. So there's one thing that I'd want to address about the evaluation function here. We are still using the overflowing to unroll our over-lengthened sentences into several parts. But what we are doing next is slightly different from the step when we are creating our training set. So here we are still doing one prediction for each of the unrolled part of our original sentence. And finally, we will yield several predictions. And how we handle this is that we compute the average for all the predictions to get one number as our final prediction for the original sample. So here we are actually testing with our test set and finding out that our test accuracy is kind of low. It's only just above 3/4. This might indicate some overfitting for our model because our validation accuracy is actually pretty high. I don't know. Theoretically, test accuracy should not be too much lower than validation, but that's the truth. And also, for a complex model like the DistilBERT, I doubt a training size of 30,000 is enough. But if we take a closer look at the confusion matrix, it actually gets more reasonable because we can detect that most of the discrepancies are associated with the neutral class. Like here, 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 and here, they are all associated with the neutral class. So how do you define a neutral sentiment? I don't really know. I mean, everyone might have a different criterion, but it's kind of ambiguous. So let's proceed to see some prediction samples, and this might explain things a little bit more. So here, I have done 15 examples, and there are two mistakes. The first one being this sentence. I feel your pain. I once lived in an apartment for 6 months where the previous tenant had 4 cats, burning eyes, and tight lungs. I'd say, in my opinion, this should be a negative sentiment, which should have a 0 as the label. And I think 8 out of 10 persons will say this is negative, but our label says it's neutral. The model prediction is as expected by us, it's 0 since negative, but I don't know, the label is neutral. And the next one is this one being the 7th one. Slept in, woke up with an iced coffee, lazed about, and went out for a late lunch with the boyfriend. It's been a sweet little laid-back Saturday. I think there is no dispute this must be a positive sentiment. But our label says it's neutral. I'm not sure why. And actually, our model agreed with me. It also says it's positive. But yeah, that's kind of interesting. So I'd say at least our model has a satisfiable performance and it's actually useful. So yeah, that's all for today, and I might go further to tweak more about the hyperparameters to see if we can end up with a higher accuracy. And yeah, this dataset, I do recommend it because it's quite balanced between the 3 labels, and the quality of the text is actually quite high. And as for the labels, that's kind of a subjective thing, and I won't judge on that. So yeah, that's all. Thanks for watching.